Hi, remember me? I'm back. You haven't gotten rid of me yet. Student has asked me to go over some of the problems on the formative assessment on game theory. Now, I want you to do these on your own first, but I thought it would be good to do something on this. Okay, so without further ado, let's move on to, so I'm talking about the formative assessment that is it's on the VLE, final relevant formative assessment on game theory and behavioral economics. Okay, so I strongly recommend you give this quiz a try. If you haven't done so yet, do so now before watching this video. Okay, moving on. I'm going to do the first few questions, then I'm going to have to switch to a different format. First question. Question 1. The game of matching pennies, in which the even player earns £1 when both play heads or both play tails, but loses £1 when both play distinct faces, and the odd player earns £1 when they play distinct faces, but loses £1 when they play the same faces. Now, let's assume for now that they care about their financial payoffs. We didn't say anything about behavioral payoffs. Nothing in the question suggests you have to think about fairness or any of that. So let's just assume they get payoffs equal to their monetary payoffs, right? So this is a game we used to play with these pennies back before we had Minecraft and all other things. One person, we both put our pennies down on the surface, and then we'd reveal, and if they matched, the even player would win. If they didn't match, the odd player would win. And I guess you'd win the penny, or maybe you'd even win £1. Okay. We also played a game odds evens, which was essentially the same thing. Okay, so the question, so what did this game look like? Let's draw it in terms of at least the monetary payoffs. So we have players, 2 players, actions, 2 possible actions, and the payoffs. So let's call this player doesn't matter which he is, the even player. He wants the coins to match. The odd player wants the coins not to match. They each get to choose whether they want to play heads or tails. Heads is the head, the face with the side of the coin with the head on it. It's called heads. The face, maybe the queen. Tails is the other side. If both choose to play heads, then the even player will win £1. The odd player will lose £1. So we have even player is on the row here. So we say 1 for the even player, -1 for the odd player. Note these payoffs add up to 0. By the way, it's what we call a zero-sum game. If they match, again, if both put tails, even player gets 1, odd player -1. If they fail to match, even puts heads, even player puts tails, odd player puts heads. The odd player wins the £1 from the even player. So the even player loses the £1, the odd player gains it. And the same here, if even puts heads and odd puts tails. Okay, so now I have to figure out which of these statements is correct, okay? So, does this have a pure strategy Nash equilibrium? Well, okay, so, or does it have a mixed strategy Nash equilibrium? Or both, or does it have no Nash equilibrium? No Nash equilibrium, okay? I've told you that every game, or at least all the games we're going to talk about, basically every game will have some Nash equilibrium, maybe multiple. We'll have an odd number if we add up the pure and the mixed. And that's essentially because, and I'm not demanding you know this in detail, although it's discussed in the book, they'll have reaction functions, and those reaction functions must cross at some point. And they'll cross at an odd number of points. Okay, so right away I can rule out choice D has no Nash equilibrium. So D is not correct, because every game will have a Nash equilibrium. Okay, so now to figure out whether it has a pure strategy Nash equilibrium, I need to try to find what that Nash equilibrium is, or R. One method is to underline best responses. Now I think you could guess right away that this is not going to have a pure strategy Nash equilibrium. It's an anti-coordination game. When one party wins, the other loses. How could they both be making choices that they don't regret if those are unless they're randomizing. But let's just do the method. Okay, so let's underline best responses. Let's start with the row. Underline the payoffs to the best responses. The row player, the even player's best response is to heads. If the odd player, the column player plays heads, he prefers 1 to -1, so I'll underline the 1. If column player prefers tails, the even player will also prefer to play tails. He prefers 1 to -1. He wants to match. That's when he wins. Odd player, I think you can get this pretty quickly, wants the coins not to match. So if the even player plays heads, he'll prefer to play tails instead of heads. 1, second payoff is the column player's payoff. 1 is preferred to -1. If the even player, the row player plays tails, the odd player, the column player will choose to play heads because 1 is better than -1. Okay. We do not see any cell with 2 underlines in it. There is no combination of pure strategies that forms a Nash equilibrium. So I can cross off A as a pure strategy Nash equilibrium. Okay, but does it have a mixed strategy Nash equilibrium? Well, this is in fact solved in the text. I want you to not necessarily know how to compute it, but just get the sense of what it is and what it will look like. Okay, it's going to involve each player mixing between their 2 strategies. What do we mean by mixing? Playing each strategy with some probability. In this case, it's going to be playing each strategy with 1/2 probability, basically because the payoffs are basically the positive and the negatives are equal. So if the other player is just flipping the coin, I can't do it, and whatever it lands on, then, so suppose the odd player is just flipping the coin. Well then, does the even player prefer heads or tails? Well, if he plays heads, the odd player is flipping the coin, half the times the even player gets 1, half the time he gets -1. On average, he gets 0. If he plays tails, half the time he gets -1, half the time he gets 1. On average, he gets 0. Okay, so if we want to get fancy, we can call Q the probability the odd player plays heads. The even player's payoff if he plays heads is going to be 1 times Q plus -1 times 1 minus Q. And if Q is equal to 1/2, it's 1 times 1/2 plus 1 times 1 minus 1/2, or 1 times 1/2 minus 1 times 1/2, 1/2 minus 1/2 equals to 0. Okay, and this would be the utility of the even player if he plays heads, given what the other guy's doing. The utility of the even player, or the expected payoff of the even player, if he plays tails, you can see it'll be the same. Half the time he loses 1, half the time he gains 1, if the odd player is just flipping a coin. Okay, so that will also add up to 0. So the even player is indifferent between these 2. If the odd player is flipping a coin, 50% probabilities, and if the even player is flipping a coin, the odd player is indifferent between these 2. Okay, so I've over-explained this as usual. We know that this does not have a pure strategy equilibrium. It does have a mixed strategy equilibrium, but it does not have more than one mixed strategy equilibrium. There's no other probabilities that could be played here that would make the other indifferent. These mixed strategy equilibria, when they're each playing probabilities of, let's say, between the 2 strategies, that make the other indifferent and thus also willing to randomize between the 2 strategies. Okay, I'm going to do one more question in this video. The next question. And as I said, you don't need to know that much about mixed strategies. I just want you to have a general idea of how they work, what they are. You don't need to be able to compute them. Okay, I'm in a little trouble here. Okay, the next question. When a game has multiple equilibria, propose methods to sort out which one would be the most reasonable prediction. Include, or which one would be the best prediction. Include, okay, the formatting got a little off on this question, but basically because I haven't reshuffled the questions, but basically the idea is we have some games with multiple equilibria, right? We can remember these. We did an exercise in lecture. Remember the big game with all of those choices you can make, and we had 5 or 6 all along the diagonal pure strategy equilibria. Another game with multiple pure strategy equilibria as well as a mixed strategy equilibria was called the Battle of the Sexes. So if you remember the Battle of the Sexes with the kangaroo and the swan. So the kangaroo could choose ballet or boxing. Swan could choose ballet or boxing. They both preferred to be together, but given that they were going to be together, they did have preferences over where they were together. So perhaps the payoff looked something like this. If they meet together at ballet, the kangaroo gets 1 and the swan gets 2. If they meet together at boxing, the kangaroo gets 2, kangaroo prefers boxing, swan gets 1, swan prefers ballet. And if they fail to meet, neither get anything. They each get 0 payoffs. Okay? We underlining best responses. Find 2 pure strategy Nash equilibria and also 1 in mixed strategies. And there's 1 in mixed strategies, but it doesn't involve 50-50 mixing. And you can read into why that is the case. Again, I'm not going to ask you to compute it, but it would be nice if you had the intuition why that was the case. It was mixing 2/3, 1/3. Okay, so we had 3 Nash equilibria. So what were the methods? How do we solve a problem like multiple equilibria? Unfortunately, the song didn't actually tell you, it just asked the question. But I proposed a few things. One would be, is there an equilibria which makes both players better off? Well, in this case, there wouldn't be such an equilibria. But if I had changed the payoffs, so instead they both preferred ballet, then this equilibria would Pareto dominate this equilibrium. This equilibrium gives them both better payoffs than this one. And then we might predict that naturally they might coordinate on this equilibrium. Okay, I also refer to this in the context of a different game called the stag hunt game. Okay, so that was one criterion. These are called refinements. Another possible criteria was find the one that seems focal and which players are likely to believe they can coordinate on, if any. So I mentioned in that big game, we might have thought there was this claim that maybe the payoffs would make, not just that they're larger, just that they're different, that the payoffs would make some equilibria stand out. So suppose we have a game with this third possibility, and so we have 2-2 here, 2-2 here, and we have 1.99 here, 1.99 here, and everywhere else it's just 0, 0. Okay, the claim with these are 3 pure strategy equilibria. The claim was, that they, even though this one had slightly lower strategies, slightly lower payoffs, this Nash equilibrium, it might be focal because how do we know which one we're going to coordinate on? Well, there's 2 that are exactly the same and 1 that's different. Even though it pays a little bit less, it gives us something to perhaps coordinate on. Okay, and then there's the third idea of you might coordinate on a symmetric equilibria. Well, these are all symmetric in the sense that they're both playing the same, but we could imagine that in some other games, I'm not going to set it up right here because I don't want to do it on the spot, but imagine in some other games there was a Nash equilibrium here also. So here, let's suppose there was a Nash equilibrium here, Nash equilibrium here, and a Nash equilibrium, let's say, here. Well, this one would be symmetric in the sense that it would occur where they're both playing the same strategy. Okay, so these are just some ideas of focal points. Okay, one more question. I think I already said that, but I want to do one more, and then we'll switch. Okay. So the correct answer was basically all of the above. Okay, it may not have come out as above in your thing, but I think you got the point that it was supposed to be all of these answers. Okay. final one I'm going to do for now. Question 3. Just going to check the video, see if it's still recording. Yep. Question 3. Okay, you're presented a payoff matrix, which I shall depict for you right now. Okay, this has, I use the language of an entry game, but here it's a simultaneous game. And remember that when I talked about entry, I was saying that one of the interesting applications of game theory was firms choosing to enter a market. When there are different competing firms, which ones will choose to enter which markets? So game theory is applied to that. All right. So let's draw this. We have two players, the row player and the column player. The actions they can take. The column player has only two strategies, enter and do not enter, don't enter. Row player has three strategies, enter fully, enter partially, and finally don't enter. Okay, now we just need to specify the payoffs. Okay, it's a simultaneous game. So they both make their choice at the same time. Let's specify the payoffs. So if one enters and the other enters fully, I'm just going to draw in the payoffs, okay? So there's a negative, seems to be a negative payoff if they both enter or enter fully. Maybe you could justify this by saying they're going to compete their prices down to a perfectly competitive or low profit price. If one enters, the other doesn't. The one who enters gains a lot. The one who doesn't ends up with 0 here. Enter partially. Okay, they seem to be splitting the gains. If one enters partially, the other doesn't, he gets some share of the gains he would have gotten if he or she were the only firm entering. Then finally, if the row player doesn't enter, and the column player enters, row player gets nothing, column player gets this whole payoff, maybe the whole market. If neither enter, neither get anything. Okay. So it's asking us about several things here, about rationalizable strategies and about Nash equilibria. Okay, so let's look at rationalizable first. If you remember, we derived rationalizable strategies basically by using this method of iterated strict dominance. So I need to see if any strategies are dominated for either player, strictly dominated. Is there one strategy that yields a lower payoff than some other strategy, no matter what the other does? I've spotted one. Okay? Have you spotted it too? Let's look at this right here. Don't enter. Okay? It looks like the row player will always do better by choosing enter partially than by choosing don't enter. If the column chooses to enter and the row enters partially, row gets 1. If he doesn't enter, he gets 0. The column doesn't enter and the row enters partially, she gets 2. If she doesn't enter, she gets 0. So enter partially, no matter what you think, what row thinks column's going to do, enter partially is better than don't enter. So we could say enter partially for, we could say for, just to be clear, for a row, that's an R, enter partially dominates don't enter. All right, sometimes I'll say D to say strictly dominates. It's strictly greater payoffs no matter what you think that column's going to do. Cross this off. Now we can talk about the iterated. Okay, is there anything more we can get? Now we could look at column. Columns, realizing that row is rational. If we have common knowledge of rationality, column will realize row is rational. Column will rule out row playing don't enter. So then column will say, all right, well, I know that row is either going to do one of these two things if I know that row is rational. Given that, is one of my two strategies always better than the other, or is either dominated by another one? Well, that doesn't seem to be the case, okay? So for row, for column, if column plays enter, sorry, if column plays enter, he gets -2 if row enters fully, or 3 if row enters partially. Let me say it another way. If row enters fully, column is better off not entering. If row enters partially, column is better off entering. So it doesn't seem like anything, so it's, in fact, nothing is dominated and nothing is dominant for column, even after we've removed this strategy of row. So iterated strict dominance doesn't necessarily get us to some unique solution. Okay. So now let's start looking at the answers. Can we rule any out? Okay. Well, there's one that's talking about rationalizability. So B is all strategies are rationalizable for either player. Well, that's not true. Right? So I can cross off B, because don't enter is not rationalizable for the row player. So B cannot be the correct answer. Okay. Okay, there's another one about rationalizability. D. Enter fully, it says, and enter partially are rationalizable for row. Seems to be the case. They've survived iterated strict dominance. And enter and don't enter are rationalizable for column. Well, they've survived iterated strict dominance, so they're rationalizable. I'm going to tentatively say that, at least on my version, I think it randomizes the answer. So if I just say D, it's not going to be clear to you. There might be a little confusion there. But the answer, enter fully and enter partially, are rationalizable for row, and enter and don't enter are rationalizable for column. I'm going to say that seems like the right answer. But let's just look at the other ones, okay? Okay, so if I want to consider A, C, and E, I have to consider how many Nash equilibria there are, or how many Nash equilibria there are in pure strategies, okay? Now I could start this from the beginning, but one thing I know is that if a strategy is strictly dominated, it will not be part of a Nash equilibrium, okay? In fact, if it's iterated dominated, it would also not be part of a Nash equilibrium. Okay. And I think you can imagine why. If it's a never best response, how could this be the point where best responses meet? So I'm going to start by not even worrying about that, and I'm just going to use the underline method. If row enters fully, column's best response is to not enter, 0 versus -2. If row enters partially, column's best response is to enter. I think we just covered this. What about row's best response? If column enters, then row's best response is to enter partially. We seem to have at least one Nash equilibrium here. If column doesn't enter, then row's best response is to enter fully. Did I make an error here? Yes, I did. We all make mistakes. Don't feel too bad when you do, okay? Let me say this again. No, I did not make a mistake. I was correct. Yeah. When column chooses enter, row's best response is to enter partially. When row chooses to enter partially, column's best response is to enter. So this is a Nash equilibrium. When column chooses not to enter, row's best response is to enter fully. This is also a Nash equilibrium. Okay? So we know there's at least 2 Nash equilibria in pure strategies. In fact, there are 2 Nash equilibria in pure strategies. And there will also be one in mixed strategies, because we always have an odd number of Nash equilibria. So C is also correct. Okay? I believe this one allowed you, yeah, I think the question said there are 2 correct answers, if I'm right. Let's double check that. Choose 2. It said choose 2. So C and D are correct. What about A? There's only one Nash equilibrium? No. What about E? There are no Nash equilibrium in pure strategies? Well, we found 2. Okay. That went a bit longer than I thought, but I hope it's helpful. I will continue this in a different video.